Hi, this video is an introduction to the concept of graph traversal that we're going to delve into in the next few videos. The goal of graph traversal is to traverse a graph, just like the name says. That means that we are trying to visit every vertex in some defined order. Remember that we covered tree traversal in the context of binary trees earlier, and there are three classical ways of traversing a binary tree: pre-order, in-order, post-order. We went into those in some depth. However, those algorithms do not apply to general graphs. There are two big reasons why tree traversal algorithms, pre-order, in-order, post-order, cannot work on general graphs, so we're going to have to develop different new algorithms. One of those issues is that a tree has a root, but a general graph does not have a defined starting point. So all of those tree traversals are organized around a defined root vertex, but graphs don't have a defined root or any other internally defined anchor vertex. Another big issue is that the Euler tour is not defined for a general graph. The Euler tour was that idea of going around the shoreline of a tree. You can do that in a tree, but in a graph there can be a cycle, and if there's a cycle in the graph, the Euler tour is not a defined concept anymore. To illustrate these two issues, first let's look at the root issue. On the left we have a binary tree, and of course the topmost node is the root, and that just defines a natural starting and ending point of a traversal. On the right we have an example of an undirected graph, and it does not have any kind of root. So it's not obvious if we say traverse this graph, do we start at vertex 0 or 4 or 2? Where do we start? And the other issue is that the Euler tour is not a defined concept in a general graph like this one. This one has at least one cycle. It has a few cycles actually, and that's going to make the Euler tour not well defined. I could do my best to try to create that Euler tour and draw the shoreline around the graph, but the problem is that it doesn't cover every vertex on both sides. Remember, the way that pre-order, in-order, post-order are defined is form the Euler tour and then decide whether you visit a vertex on the left side, underneath, or the right side. But due to this cycle in the center, the blue shoreline is cut off from the interior of the graph, and we can never get at those other sides of these vertices. So it just doesn't work. So what we're going to develop in the next couple of videos are graph traversals that actually do work. The tree traversal algorithms, pre-order, in-order, post-order, just don't work. We're going to have to come up with something different, a different traversal method. The graph traversal algorithms take a start vertex as input. So with a binary tree, you can just say traverse this graph. The only input into that algorithm is the tree itself. But with graph traversal, we have to give two inputs: the graph to traverse and also which vertex to start from. That means that every graph can have multiple possible traversals, one traversal from every different vertex starting point. There are two classical graph traversal algorithms that we're going to cover. The first is called depth first search, and we often call this DFS, just the acronym of the first letter of each of those words. And it's called that because it prioritizes going deep away from the start vertex first. The other alternative, the other big classic, is called breadth first search, which we often call BFS. Again, it's just the acronym of those words. The BFS algorithm prioritizes going broadly in all directions away from the start vertex at the same time. And we'll see in subsequent videos that these are fast algorithms. They can be implemented to take linear time. In a graph with n vertices and m edges, each of these algorithms takes big O of n plus m time. So that's linear time, a very fast efficiency class that's proportional to the amount of time it takes to actually look at every vertex and edge in the graph. So this traversal does not really add any overhead. This sketch just kind of gives you the feeling of the two traversals. We are going to go into this in quite a lot more detail soon, but depth first search starts at a designated start vertex, and then it kind of plunges deep into the graph. So this cloud is representing a big graph. It goes off in one direction as far as it can until it reaches a dead end, and then it backtracks a little bit to keep going. So that's depth first search. That's why it's called that, because it goes deeply as quick as it can. Breadth first search has a different approach. It also has a designated start vertex, and we visit that vertex, and then all of the vertices nearby, and then all of the vertices a little further away, and then a little further away in this kind of spiraling outward approach that is broad or achieves breadth of coverage early on.